Okay, so we're going to start off the trig unit, right, trig chapter with the Pythagorean theorem. And so if you're entering a high school geometry class, you probably have seen the Pythagorean theorem before. It's usually introduced prior to getting here. So we're not going to spend a lot of time actually doing normal Pythagorean theorem problems. We're going to focus on things like word problems instead, right? But let's just quickly introduce what the Pythagorean theorem is for anybody that maybe hasn't seen it before, okay? So when we're doing the Pythagorean theorem, they're claiming that if we're in a right triangle, so this only works for right triangles, right? If we're in a right triangle, that they're claiming there's a relationship between the two legs and the hypotenuse. So let's just quickly define what those things are, the two legs and the hypotenuse, right? So they're saying if A and B are the lengths of the legs, okay? So if I'm coming over to my picture over here, I've labeled it for you. If I have a right triangle, we put the right angle in the corner, okay? The legs are the two sides that create the right angle. So if you notice, if I draw the kind of highlight around the two legs, I make the right angle. In the Pythagorean theorem, it says if you square the two legs, a squared and b squared, right? If I square the two legs and I add those two squares together, that it should always be the same as the hypotenuse squared. So what's the hypotenuse? Okay, the hypotenuse is that third side. So if you notice, I have this side right here. Okay, that is not connected to the right angle. In fact, what it is it's across from the right angle. If I travel through the triangle, I hit the hypotenuse. Okay, so if you first thing you have to do is you have to be able to identify these sides. Okay, so if we plug these values in, a squared, b squared, and c squared, into the Pythagorean theorem, it should always be true in right triangles. Okay, so we're going to come down and just look at some very basic examples. I'm not going to do all of these. In fact, I'm going to try to just highlight the ones that are kind of the most intimidating looking, right, and we'll go from there. So we'll do one simple problem. In this particular example here, if I'm using the Pythagorean theorem, right, I'm going to first identify what it is that I know, right, and then once I identify what I know, we'll plug into the Pythagorean theorem. So again, I'm going to highlight what I know. In this case, I know a 5 and the 12, and if I'm looking at that both of those are surrounding the right angle, and that means that these two sides are the legs. So if I'm plugging into the Pythagorean theorem, which says a squared plus b squared equals c squared, I know a and b. So I'm going to plug in 5 squared plus 12 squared equals c squared, right? I'll just call this side c, right? And so this says now 25 plus 144 equals c squared. Well, 25 and 144 is 169, okay? And then to solve for c, to get rid of a squared, I'm going to use its opposite, which is square rooting, and I find out that c is equal to the square root of 169 is a nice number. It's 13. So I know that this side is 13. Okay? This problem over here on the right is the identical type of problem, so we're not going to do that one. Okay? Problem 3 is the same situation again, but in this problem there's a little twist, and that's that one of the sides is not written as a nice kind of simple integer. It's got a radical in it, right? So again, if I'm looking at this, I see that I definitely have the two legs because I'm surrounding the right angle again. So I'm going to plug in just the same. I'm going to say 2 square root of 3 squared plus 2 squared equals, again, we don't know the hypotenuse, which we typically refer to as c when we're dealing with the Pythagorean theorem. So really the twist with this one, the strange thing is, how do I handle squaring 2 square root of 3? Okay, and the answer to that is I'm actually going to square the 2 and square the square root of 3, right, and then simplify. So 2 squared is 4. The square root of 3 squared, square rooting and squaring are opposite, so they're just going to undo each other, and I'm going to be left with just the 3. Okay, and then 2 squared is 4. Okay, so this says 12. When I multiply these together, 12 plus 4 equals c squared. Well, 12 and 4 is 16. And so it looks like our c has to be 4. Right? So again, you might have problems where you have to square a slightly more complex expression, and if you do that, just square the parts. Okay? So let's take a look at this problem over here, because now we're getting into a situation where if I highlight around the right angle, like we have been, now we're running into the problem where, it doesn't look like I know one of the legs. In this case, I know the hypotenuse. So when I plug into this problem, I'm going to call this A, and you could very easily call this B. In what order you plug in A and B does not matter, right? So I'm going to say A squared plus 7 squared is equal to 25 squared, okay? So now I just have to simplify and solve for A. It's just a little bit different solving. It's going to be A squared plus 49, and if you do 25 squared, it's 25 times 25, 625, okay? And then I need to just solve this. So I'm going to subtract 49 from both sides, okay, which is equal to 576. So I'd say a squared is equal to 576. And then I can square root 576, and I find out that that's equal to 24. Right? So I can solve this one. It's just that I need to make sure that I plug into the right spots to get my answer. Okay, so these problems down here are very similar in nature. The only thing that I'll say about these ones is if you want to try them on your own, you might get an answer that is a square root. Like for example, you might get something like the square root of 24. Right? If you get something like the square root of 24, make sure you simplify your radicals. We always leave them in simplest radical form unless we're otherwise told to do something else. Okay, so before we move to the next slide, I want to highlight this first problem here. It's and just point out that we had a nice integer answer come out of this, right? We had an integer of 5 and an integer of 12 as the legs, and the hypotenuse came out to be a nice integer as well. It came out to be 13. Okay? And if you take a look at this problem over here, the same thing happened. My hypotenuse was a nice integer of 25. The leg was 7. I got another nice integer back. Okay? When that happens, that all three legs of a right triangle are integers, we have a special name for those, and we call those Pythagorean triples. Right? So Pythagorean triples are just all three numbers, the two legs and the hypotenuse are are integers in a right triangle. And so I've given you a list on the left-hand side of what we call the base triples. Okay, the simple triples, right? If you notice 3, 4, 5, if you do 3 squared plus 4 squared, 5 squared, it does work out. If I plug this into the Pythagorean theorem, 5 squared plus 12 squared, 13 squared, that's the one that we just saw. 8 squared plus 15 squared equals 17 squared, it works. 7 squared plus 24 squared, 25 squared, right? So these are ones that are nice, simple. If I plug them into Pythagorean theorem, they do work, okay? So here's what the claim is, okay? If I come down to this problem, and I ever see a right triangle where one of the legs is 3, and the hypotenuse is 5, that's this triple up here that I know without ever having to do the Pythagorean theorem that this has got to be 4, right? So the Pythagorean triples are a nice way that we can fill in the blanks and just know what the answer is without ever having to actually use the Pythagorean theorem. So knowing just this, the beginning of this list, these first 4, right? There's like I think an infinite number of triples, right? There's definitely a lot of them. As long as you know the first few, it can be very helpful, especially the 3, 4, 5, 5, 12, 13. Those ones will show up a lot in things like SATs and the like, right? So if you see this, the right-hand side here, the claim is, what we're pointing out here is that not only is a 3, 4, 5 a triple, but any multiple of 3, 4, and 5. If I scale up 3, 4, and 5, like for example, in this case, if I multiply this by 2, and this by 2, and this by 2, 3 times 2, 4 times 2, 5 times 2 is 6, 8, 10. That I know that if a 3, 4, 5 is a triple, that any multiple is also a triple. So again, if you come down to this example here, 60 and 80 are 3 times 20 and 4 times 20. So I know right away that this leg right here has to be 5 times 20, which is 100. Right? So we can use these to help us out. Same thing with this second example here. Okay, if you notice, this 26 is 13 times 2. And this 10 is 5 times 2, and so I know this side over here has to be 12 times 2. I can complete the triple, and as you get used to them and you start seeing them, you'll start to pick them out, and you'll notice, especially 3, 4, 5, and 5, 12, 13 show up a lot, right? So it's just kind of a nice shortcut that we can use to help us out, okay? So we're going to do a couple of word problems just to kind of apply this idea of the Pythagorean theorem to some advanced problems, okay? So this example here, they're saying a flagpole has cracked 9 feet from the ground and it fell over as if hinged. So what does that mean, right? So we're going to draw a flagpole. We're kind of saying there's this flagpole, okay, and it broke, right? So at some point it broke and it fell over, right, and it's kind of laying like that, okay? And then there's the ground, right? So if you notice, here's our nice right triangle that we want to see. We're assuming that the flagpole's standing straight up, okay? So they're saying 9 feet from the ground, the flagpole cracked, okay, and it hit the ground 12 feet from the base. The base of something is where it's connected to the ground, right? So we're going to say from the base of the flagpole, okay, and if we measure out 12 feet, that's where it hit. So this is 12, okay? And they want to know how long was the flagpole, so we really have to find this little section of the flagpole, and that's going to help us to figure out how tall the entire flagpole was before it fell, right? So here's the nice thing about this. 9 and 12, right? I'm just going to write this one out. 9 is 3 times 3, okay? 12 is 4 times 3, and that means that the third side has to be 5 times 3. This is a triple. 9, 12, 15. I can solve this one very simply without ever having to use the Pythagorean theorem if you recognize the triples. Okay, so I know that the entire flagpole is 9 plus 15, okay, which is 24 feet. Okay, so the final answer to their question is 9 plus 15. The part that's still standing plus the part that cracked is the entire length of the flagpole. But if you notice, that problem is very easy, very straightforward, because I recognize the triple 9, 12, 15. Again, which again will come with time. Okay, so here's the second one, and we'll end with this one. All right, they're saying there's a building. So let me draw my building. All right, so I have a building. Here we go, standing straight up, and they're saying there's a ladder leaning against the building. All right, so let's draw our ladder. All right, and again, the ground is a thing, so let's make sure we draw on the ground. Okay, and so they're saying in this problem, 12-foot ladder. So this is my ladder. This is 12. Okay, and again, it's saying it's placed 4 feet from the building. So if I measure from the building to the base of the ladder, this is 4. Okay. So if I'm looking at this one, this one's not a triple. You can take a look at the triples that we know. This is not a triple. They want to know how far up the building the ladder hits, right? So we're kind of measuring this little section of the building here. So I'm just going to have to plug into the Pythagorean theorem for this one. 4 squared plus x squared. Let me fix my squared. Okay. Is equal to 12 squared. Okay. Again, we're assuming that the building's standing pretty straight up, so my right angle's right here. So this says 16 plus x squared equals 144, right? And then I gotta get that 16 onto the other side. So this is going to be 128. X squared equals 128, and I can square root both sides. So this is a good example to see, because in this case, 128 is not a perfect square, but it is made up of a perfect square and another number. In this case, it's 64 times 2. And I can square root at least the 64 factor and turn this into simplest radical form, 8 times the square root of 2. So we'll leave it as 8 square root of 2 feet. And if someone wants to use this to do something else, they can turn it into a decimal if they'd like. But we're always going to leave our answers in simplest radical form. Right? So there's a lot more examples that we can do with this, but we're going to stop there and say, you know, good firm application of the Pythagorean theorem. Right? And we were going to do some more expansion on this idea of the Pythagorean theorem when we talk about the converse and some of its other applications.